Detecting undefined behavior across Rust FFI.
Attending this talk. I want to start with an apology actually. Like if you hear me slowing down with voice, it's because I haven't slept for 24 hours due to weather and flight cancelling and finding trains and places to come here in time. So yeah, without no further ado, so today I'm going to talk about how to detect undefined behavior in Rust FFI, our approach, and possible other problems that the research community can still tackle. And then what's a talk about Rust without talking a little bit about C first. Also, as a note, this is a work in progress, so we just have few preliminary results. There's still plenty of stuff to do. Would really appreciate your feedback and maybe potentially searching for collaborations. Okay. Right, so we've been programming for a few decades now. Great, we have C that has given us amazing systems, large-scale systems. Most of the systems we have today are written in C, and despite decades of fantastic research going into how to verify C, we are still troubled by lots of memory safety issues. So then, inspired by the verification community as well as by the language designers and advancing languages, we have now safer languages such as Rust and Spark and so on, which promise us a slightly safer, better world when building systems. And for that, like perhaps one of the most popular in the last decade or so has been Rust. There has been a lot of encouragement from both academia and industry to actually slowly move towards these safer languages. A lot of adoption in industry, which led subsequently to quite a few works, again, both in industry and academia, that tackle the translation from C to Rust. So there's a lot of different works at the moment tackling C to Rust translation. They come with different
Take the normal microphone first?
Yes. Yeah, we'll probably...
Oh, works. Okay.
Turn down the volume.
Thanks. All right. So as we are moving from C to Rust, there's also, we have a new set of memory safety issues now because we have two systems written in different programming languages with two different memory models that have to interact in what we hope it's a safe way. So then we have new works that aim to actually make this, make sure that the bridge between Rust and C is safer. Now, are we safe at this point? Lots of work done to become safer. We have a totally and completely new class of issues and memory safety issues that we have to tackle now. So we have Rust and C. They often, they work with different memory data layouts representation, different alignments. Interpreting one data type written in Rust differently in C can definitely lead to undefined behavior. Then you have error handling in Rust, which is used with a dedicated data structure, And in general, in C, you use numeric opcodes or global states and so on to denote errors. Misinterpreting those numbers in Rust can also lead to undefined behavior. Then you have panics and unwinding. So Rust treats panics quite nicely. Once you have panics, it unwinds the stack for you, and trying to do that while having a call into C, which doesn't do that, can again lead to issues into C, which does not expect the stack to be unwinded. So you might end up in an inconsistent program state. Then of course you have lots of synchronization issues because the concurrency models are different. And then you have like the bread and butter of Rust, which is memory, ownership, and lifetime. So in Rust, a value always has one owner. There's no such thing as ownership or lifetime in Rust. So lifetime represents the lifetime of a reference. So a reference is similar to a pointer, but you have some additional constraints in Rust that are enforced by the type checker. Then you might have undefined behavior that leak across boundary. Those might also affect Rust safety. And then you have very strict aliasing model in Rust, which again is not enforced in C. So we go towards a safer world, but now there's a new class of issues that we need to tackle. So at least for the type mismatch, we have quite nice bindings these days that make sure that the types are aligned. But for memory safety, we don't have that much tool support at the moment to ensure that the strong disciplines in Rust are actually enforced by C. So it's actually, we go back to being the developer's responsibility to avoid undefined behavior in FFI by maintaining Rust types invariant. So we kind of go back, but not really back, because what Rust still allows us is to kind of minimize the space in which these issues can occur. So yes, we can still have undefined behaviors and issues and memory safety issues, but the search space for detecting these issues is much smaller these days. All right. So there's quite a bit of work for verifying and detecting undefined behavior in unsafe Rust. There are amazing tools and even theoretical frameworks. Many people know of Rustbelt, PriSC from Aeneas, Crusoe, Kani, Mirai. So there's plenty of tools that are allowing us to offer a framework for verifying or checking undefined behavior in unsafe Rust. But this is just unsafe Rust. What I'm building towards is Rust plus C. So we need to somehow extend these technologies to also interact with C contracts or with C behavior. Then for bug detection tools, we have MIRI, which is the most used bug detection tool for unsafe Rust. So MIRI is an interpreter that implements the stack borrows discipline. So what's a stack borrow discipline in Rust? It's a model that allows us to define the aliasing discipline in Rust and checks whether any of the unsafe code violates these disciplines. So that's great. It's highly used. There's a database of all the different bugs and issues that MIRI has detected, so very practical. However, it does not extend to C. So again, we stay only in the Rust world. There was an effort a couple of years ago to extend MIRI to C by working at the LLVM level, and that has produced good results. However, it's really slow, since both MIRI and MIRI LLI are interpreters. They assume a good test suite in order to function properly. All right, so this is kind of the background so far. Let's see quickly what are the safety pillars of Rust type system. So let's consider this very simple three-liner program. What I mentioned earlier is that every value in Rust, every value in Rust has one owner. So what that means is that at any one point, any value can only be is owned by exactly one variable. So that variable is the only one that can, say, deallocate or free if heap is involved. Heap that free that memory. Then we have another thing specific to Rust and few other languages, which is mutability. So you can explicitly mention whether the value can be mutated or not. You also have borrowing, which is slightly different than the pointers in C. So borrowing, the first borrowing in the second line, it's a read-only reference. So it allows us to read, it creates a reference to that memory location with read-only permission, as well as reading with mutability permissions. Now, all these together, these disciplines form the core of Rust memory safety by abiding to these safety principles that combine the few disciplines. So the first safety discipline, as I mentioned, is that every value has a single owner. And second one is that the lender needs to outlive all of its alive references. So there can be no reference pointing to something that no longer exists, in other words, so that avoids dangling pointers. Then a mutable borrow can only be created if its lender has no other borrows living. So that's in general, at least in the concurrent setup, is to avoid two threads to, say, avoid data races, like two threads modifying the same value at the same time. And finally, the lender cannot be modified as long as one of its shared borrowers is still alive. So in other words, at any one point you can have multiple shared references, but exactly only one mutable reference. All right, now let's go back to C and look at a very simple program. We have a function, add1, a method that simply takes in a reference to an integer and increments it by 1. So simple, we expect here to, given this program, we expect here to be, this line to print 42. Now the equivalent Rust program would be written as so. However, if I'm just passing this to Rust, just to exhibit a little bit the mutability, Rust will complain at this point because I only gave an immutable read-only permission. So I'm not allowed to mutate. Super great. The compiler complains you cannot do that. And in order to mutate, you have to change and add a mutability annotation. Now, what happens if instead of doing that, I'm simply adding, I already have a library that adds one defined in C. I only have one library. I already have a library that does the functionality I'm searching for, namely adding one. So I'm doing that, and as you guess, nothing actually happens. I can compile and run this just run this program, and I'm expecting here to have to print 41 because I know that I cannot be mutated. Yet if we run this program, we will have 42 there, which is a very simple undefined behavior, but with complicated paths, this can lead to pretty much a lot of undefined behavior and chaos. So this is the sort of problems we are trying to tackle, like how to enforce that the type disciplines of Rust are actually respected by C. And to complicate things a little bit further, as I mentioned earlier, only the owner can free memory. But if you're calling functions, if you're calling into C, and C does not have the notion of ownership, it could be that on a certain path you will have a free here, while what Rust does once P goes out of scope, so So what does it mean? That once the owner goes out of scope of some value allocated on the heap, that value will be automatically freed. So what happens here is that there will be at one of the intermediate representation, the compiler inserts a free and will free P. Well, that has also been freed on a certain path in the FFI. So at this point, you could have a double free on a certain path. Right, so to go quickly through our solution for this problem. So we are trying to use the type information that we have. So Rust has a very rich type system information. And we're thinking, can we leverage this type information somehow to check whether there's any violation of the expected behavior by the set function? So we take the type information and we translate it into a dynamic test and then just test whether that value is as expected, right? So in this case, say I have, I'm creating a copy of the value that was stored in I, and I'm just checking whether the value that I points to is the same as X. So this looks a little bit naive, and it will be difficult to extend to other properties, say beyond mutability, if I have something like aliasing and so on. So instead, what we do, instead of just checking the execution effect, we actually check what happens at each step in the execution. How do we do that? We actually have an interpreter already that does that, which is MIRI LLI. So what we basically do is we use the type information to generate a property-based test. Why a property-based test? Because that allows me to fuzz through a lot of different values. Then we use MIRI to guide the execution towards the FFI call, at which point we use MIRI LLI to check whether the property in the PBT is as expected. Okay, so how is this different than MIRI, LLI, MIRI PBT, so many things? Well, what MIRI does in order to check for an undefined behavior, if this is a Rust crate, it quantifies over the entire, like it tries to capture the execution of the entire crate, assuming you have a really good test suite that is able to quantify over the entire crate. While MIRI LLI does exactly the same thing, hoping that at some point it hits the FFI, right? Our goal is to, instead of doing this big search space, is to reduce the search space to only this hot area where we note that some issues might happen. So that's basically the goal of MIRI PBT. And we have some preliminary results. We tried to run MIRI and MIRI LLI on the same data set. There were no new bugs there, but once we tried and we introduced some random freeze or some random operations inside the C call, MIRI PBT was able to find almost all the bugs, while MIRI LLI was not able, because it's not able to quantify over the entire space, search space of C. Okay, so our goal with MIRI PBT was to find undefined behavior in the Rust C FFI, and we do that with, our aim is to reduce the human effort by reducing the number of test cases. This has been developed by colleagues at TU Delft, Julius and Jana, and we want to do way more than that. We have a static analysis plan that is quite long, and I don't have time to go through it, but I'm very happy to explain why we need a static approach, and finally not a static approach, but a hybrid approach where we do both static and dynamic checks. And with that, I conclude.
So,
Thank you.
are there any questions? Oh, by the way, can the next speaker try to prepare herself or himself? Who? Question?
Thank you. Quick question, I'm not quite sure. How do you invoke the FFI if you don't go through a test from the crate? How can you be sure that you supply correct parameters that won't just crash the FFI because of violated invariance?
So that's a great point. First, yes, it can crash without the proper, if the types, like it can be in an inconsistent state. And indeed, so we are still using MIRI to reach that state. So we are still crafting a test suite to reach the FFI, but then inside the FFI we need nothing. So that is automatically generated. So there's still, okay, and there is where actually the second part of the static analysis comes into play, because the static analysis is supposed to collect all the constraints that allows me then to fuzz through the context. So I fuzz the context, and then I fuzz the FFI, and yeah, but I happy to chat more during the break.
One more question?
Who was?
Hello. Hello. Oh.
I'm happy to.
I was going to ask you to go back a few slides.
Oh, sure.
But if we don't have time, I can ask you offline.
I can definitely join you with my laptop offline, or if I can answer without the slides, I'm also happy while they install.
I was just wondering, in the example, the add one
Yes.
thing, and you had star I.
Yes.
Can't the compiler optimize that and assume that no
Yes.
one has modified I since you haven't
Exactly.
given?
That's the problem. Exactly. The compiler optimizes, uses that information to optimize the program, and subsequently leads to undefined behavior if actually the C function is
Yeah,
modifying.
but so does your assert EQ actually do anything then if the compiler optimizes?
Again, please.
I'll talk to you offline.
Okay, sure. I have to pass you this, I think.